Hello everyone. So, today is the first lecture on limits. So, today I will explain what do we mean by limits. So, limits are very important concepts and it is the backbone of whole of calculus. So, this is very important chapter for you. So, let me start with the definition of limit. So, suppose f is a function defined on an interval containing x equal to a except possibly at x equal to a. So, we would like to define what do we mean by the limit of the function f of x as x tends to a. So, the notation for this is notation we will use is for the limit we write LIM limit as x tends to a of the function f of x, right. This denotes the limit of f of x as x tends to a. So, informally what it means is formally the limit lim x tends to a f of x is the real number L such that f x is arbitrarily close to L if x is chosen to be sufficiently close to a. Of course, excluding the point x equal to a. So, let me explain what we mean by this arbitrarily close to L and sufficiently close to a. So, suppose I have a function and we have x equal to a here and this function is something like this. It might not be defined at a. So, if we look at this definition, the limit of f x as x tends to a, this is this number L such that if you want the value of f x to be as close to L as you want. So, suppose I want my f of x to be in this interval containing this point L, then from this picture you can see that if I choose my x to lie in this interval, then if x belongs here, x lies in this interval, then f of x lies in this interval. Let me call this interval as I, lies in the interval I. So, in case there is no such L, then we say that limit f of x, x tends to a, this does not exist. And if there is such an L, then we will say that the limit is equal to L. So, for example, if I look at this function, so let me write example 1. Suppose I have this function f of x which is equal to 0 for x less than 0 and it is equal to 1 for x bigger than 0. So, this is a function f x equal to zero if x is less than 0 and this is 1 if x is greater than equal to 0. So, now here if you see, so does limit f of x as x approaches 0 exist? So, in this case if you see, if I take my x to be in any interval containing 0, then for positive x we know that the value of f of x is 1 and for any negative x, no matter how small it is, we have this is equal to 0. So, in this case the answer is no. Because for x greater than 0, f x is equal to 1 and for x less than 0, f x is always 0. So, no value of L will satisfy our requirement. So, there is also concept of one-sided limits. So, in this case let me define one-sided limits. So, there are two, one is called left hand limit and the second one is right hand limit. So, what is left hand limit? So, this we will use the notation limit of f of x as x tends to a minus. This means that here we are looking at the function. So, let me again explain by this example. So, the function is 1 for x greater than 0, greater than equal to 0, and 0 for x less than 0. So, in this case, for f x equal to 0 for x less than 0, 1 for x greater than equal to 0, the left hand limit, limit x going to 0 minus of f of x is equal to 0. This is because if I take any point in this interval to the left of this point, then f x is identically equal to 0. So, left hand limit, let me write. So, limit of f x as x tends to a minus, this is equal to L if we can make f x to be arbitrarily close to L by choosing x to lie in the a sufficiently small open interval to the left of a, that is something of the form a minus delta to a for some delta positive. Similarly, we can define right hand limit this is denoted by limit of x going to a plus f of x, this is equal to L if f x can be made as close to L as we want by choosing x to lie in a small enough interval of the form a to a plus delta. So, this is called right hand limit because we are only considering the value of the function in an interval to the right of a, whereas for left hand limit we are interested in values of x in an interval to the left of a. So, note that for the left hand limit only the values of the function to the left of A is important, and similarly for the right hand limit only the values of f x to the right of A is important. Also, the value of f of A is not at all important for the purpose of knowing the limits. Whether it is limit x going to A f of x or limit left hand limit of f of x at A or the right hand limit of f of x at A. So, another remark is that the limit of f of x at x as x approaches A, this is equal to L if and only if both the left hand limit and the right hand limit exist at x equal to A and are equal to L. So, the limit exists if and only if left hand limit and right hand limit both exist and both are equal to L. So, for the example, f of x is equal to 0 for x less than 0 and 1 for x greater than equal to 0. If we calculate limit of x going to 0 minus f x, the left hand limit, this is clearly equal to 0, and the limit of x going to 0 plus f of x, this is equal to 1. So, both left hand limit and right hand limit exist at 0, but since they are not equal, the limit limit x going to 0 of f of x, this does not exist. Okay, so can we have the case that even the left hand limit, left hand or right hand limit does not exist? So, in the previous example we saw that left hand limit and right hand limit exist, but they are not equal. So, the limit does not exist, but can we have this case? So, let us consider this. Let f x is equal to say sine of 1 by x for x not equal to 0. So, does limit x going to 0 plus f x exist? So, we are defining f of x for all x non-zero, and f of x is defined to be equal to sine of 1 by x. So, if you draw the graph of this function, so note that sine 1 by x is equal to 0 for all x of the form x is equal to, if I take 1 over n pi, where n is a natural number, right. We know that sine is 0 at all integer multiple of pi. So, if I take x equal to 1 by n pi, then sine 1 by x is equal to sine of 1 by x is sine of n pi, which is equal to 0, right. Also, if x is equal to 1 by 2n plus 1 pi by 2, then sine 1 by x, this is equal to sine of 2n plus 1 pi by 2, which is equal to minus 1 to the power n, right. So, if n is even, we get 1, if n is odd, then we get minus 1. In fact, if my x belongs to the interval, say, so if I take 1 by x to be in the interval say 2n pi to 2n pi plus pi by 2, then that is x is in the interval 1 by 2n pi plus pi by 2 to 1 by 2n pi, then f x equal to sine 1 by x takes all values between 0 and 1, right, because in the interval 2n pi to 2n pi plus pi by 2, sine of x takes the value from 0 to 1. In fact, if I take from 2n pi minus pi by 2 to 2n pi plus pi by 2, then it takes all the values from minus 1 to 1. So, what we see is that if you would we try to draw the graph of this x, and then I have f x equal to sine of 1 by x. So, if I am interested in the right hand limit, I need to look at the value of this function to the right of this. So, if you see, if I take some 1 by 2n pi, and then I have 1 by 2n pi plus pi by 2, then the value of this is varying from, I have 0 and let us say this is 1. So, this takes all the values from 0 to 1, and then again at 1 by 2n pi plus pi, it becomes 0 again, and then it again goes to minus 1, then it again goes to 1. So, as you go near x equal to 0, this keeps oscillating. So, what happens, the function f x keeps oscillating between minus 1 and 1 in any interval containing 0. Thus, if I am looking at right hand limit of this function, this does not exist. Similarly, the left hand limit also does not exist for this function. So, now so far I have given some intuitive notion of the limit of a function. Now, next I try to give the regress definition. So, this is also called the epsilon delta definition of limit. So, okay. So, the definition is, we say that limit of f of x as x tends to a, this exists and is equal to L if given any epsilon positive. So, if you take any real number epsilon which is positive, then there exists a real number delta which is also positive, such that if I take x to be line such that if mod x minus a is less than delta and greater than 0, then mod of f of x minus L, this should be less than epsilon. Let me highlight these things. So, let me explain this again by graph. So, we have x and y is equal to f of x, and we have some function now we have this L. So, as we explained before that the limit is that value if it exists such that if I approach this x equal to a from either left side or right side, then the value of the function becomes arbitrarily close to this number L. So, suppose I want that my f of x should be in between L minus epsilon to L plus epsilon, then I can choose a delta such that if my this is a minus delta to a plus delta, if my x is in this open interval a minus delta to a plus delta except possibly at x equal to a, then my f of x should lie in this interval L minus epsilon to L plus epsilon. For example, you might want that this epsilon is equal to say 0.1. So, if you take epsilon equal to 0.1, maybe there is some small enough interval here a minus delta to a plus delta for which the function value is between L minus 0.1 to L plus 0.1. Now, if you make this epsilon smaller say 0.01, then still there is another delta presumably smaller than the previous one, such that if I choose here, then again this is between L minus 0.01 to L plus 0.01. So, this is the definition of the limit. So, remark delta generally depends on epsilon. So, if you make epsilon smaller, then delta might have to be made smaller. So, one example, consider the function f x equal to say x square. And then what is limit of f of x as x approaches 0. So, if you see this function, this is very simple, this is a parabola. So, here if you see the left hand limit, if you approach this function from the left side, then it is approaching this point which is 0, and from the right again if you approach, then this is becoming closer and closer to 0. So, intuitively from the graph, it is clear that the limit is 0. Let us try to prove this. Using the epsilon delta definition. In this, what you have to do is, if you are given an epsilon, then you have to tell what is delta such that the condition is satisfied. So, we start with let epsilon be any positive number. What we want a delta positive such that if my mod of, let me write, so x minus 0, a is 0 here, if this is less than delta and greater than 0, this should imply that my f of x minus, we are claiming that the limit is 0, this should be less than epsilon. That is, if mod x is less than delta and greater than 0, this should imply that mod of x square is less than epsilon. Now, we see that now if mod of x is less than delta, then mod of x square, this has to be less than delta square, right. But we want that my mod x square should be less than epsilon. So, if we want mod of x square to be less than epsilon, so if we choose delta equal to square root of epsilon, then mod x less than delta, this implies mod of x square is less than delta square, which is equal to epsilon. And delta is of course positive if epsilon is positive. So, from the definition, from the epsilon delta definition, it follows that limit of x square as x goes to 0, this has to be 0. So, this was very simple example, but it was just to illustrate how we use this epsilon delta definition to prove that limit is equal to some number. Okay, next what we will do is we will see some properties of limit. So, some properties of limits. So, the first one is this sum rule. So, this says that suppose f x and g x are two functions such that the limit x going to a f of x exists and the limit x going to a g of x, this also exists. Then the conclusion is then limit of f x plus g x as x goes to a, this must exist and the limit is equal to limit of f x plus g x at x equal to a is equal to the sum of the limit of f x and g x. So, briefly it says that the limit of sum is equal to sum of the limits. Limit of sum is equal to sum of the limits, provided each limit exists. So, this again is a something which is not very hard to believe that limit of the sum is sum of the limit, but if you try to prove this, then this epsilon delta definition comes handy. So, proof. So, let limit of f of x as x goes to a, this is equal to some L 1 and limit x tends to a g of x is equal to L 2. So, by using the definition, what it means is that, and to show what we want to show is that claim is limit of f x plus g x as x tends to a, this is equal to L 1 plus L 2. So, to show this, we need to find a delta. So, let epsilon greater than 0 be given. We need to find a delta. So, first of all, we are given the limits of f x and g x. So, since limit x tends to a f of x is equal to L 1, we know that there exists some delta 1 positive such that if my mod of x minus a is less than delta 1 and greater than 0, then this should imply that mod of f x minus L 1 is less than. So, instead of epsilon I will put here epsilon by 2. because what it says is that given any epsilon you can find a delta such that this happens. So, it should be true for epsilon by 2 also. So, this is my equation 1. Similarly, I can find there exists a delta 2 positive such that mod of x minus a less than delta 2 and x not equal to a. This should imply that mod of g x minus L 2, this is less than again epsilon by 2. Let us call this 2. So, now what we have to show is we have to find a delta such that, so if I take, so now we have the function is f x plus g x and we have to prove that the limit is L 1 plus L 2. So, if we take f x plus g x minus L 1 plus L 2 and we have to make the difference in absolute value to be less than epsilon. So, this is equal to mod of f x minus L 1 plus g x minus L 2 and then we know that mod of a plus b. So, this is less than equal to mod of f x minus L 1 plus mod of g x minus L 2. This is because mod of a plus b is always less than equal to mod a plus mod b. Now, what we are given from 1 mod of f x minus L 1, this is less than epsilon by 2 if mod of x minus a is less than delta 1 and this is less than again epsilon by 2 if mod of x minus a is greater than 0 and less than delta 1 and also mod of x minus a is greater than 0 and less than delta 2. This is from 1 and 2. And this sum is equal to epsilon. So, if I choose delta to be equal to the minimum of delta 1 and delta 2, then if mod x minus a is greater than 0 and less than delta, then because delta is the minimum, mod x minus a is less than delta 1 as well as delta 2. This will imply that mod of f x plus g x minus L 1 plus L 2, this is less than epsilon. Thus, by definition, limit of f x plus g x is equal to L 1 plus L 2. Okay, so, this rule will be very important because very useful because if you know the individual limits, then you can find limit of the sum of functions. Right. Second property, limit of, if I take any alpha times f of x as x goes to a, this is equal to alpha times limit of x going to a f of x where alpha is any real number and this is true if the limit of f of x as x goes to a this exists, right. So, if I multiply the function by any real number, then the limit of this constant times f of x is equal to the constant times limit of f of x. So, that is limit of a constant times f of x equals the constant times the limit of f of x. Right. So, proof we will not do, proof I will leave it as an exercise. So, again using the epsilon delta definition, you should try to find what is the delta which will work for this. Okay. So, and the third one is of course, just like the sum rule, if I take difference, limit of f x minus g x, this is equal to limit of f x minus limit of g of x, provided the limits on the right hand side exist. This is just like the sum rule, if limit of f x and limit of g x exist, then the limit of the difference is equal to difference of the limit, and this in fact follows from property 1 and 2. Of course, one can prove directly also using epsilon delta definition, but let me show that this actually follows from 1 and 2. So, we have f x minus g x, you simply write this as f x plus the constant minus 1 times g of x, right. So, now we have sum of two functions f x and minus 1 times g of x. So, since this is true, limit of f x minus g of x is equal to limit of f of x plus limit of minus 1 times g of x. This is by 1, property 1, sum rule, and then by the second property, limit of minus 1 times g of x is minus 1 times limit of g of x. So, that is limit of f of x minus limit of g of x. Okay, so this brings to the end of first lecture. In the second lecture, I will show some more properties of limits, and then we will also do some more examples and calculate some limits. Thank you.